Welcome to episode 8. As you may have noticed in previous episodes, PlanetSmith uses real-time lighting. As the planet rotates, the sun rises above the horizon. This gives us an awesome effect, causing hills to cast fast shadows, which recede quickly as the sun rises higher into the sky. Also, it's not just full blocks that cast shadows. Even leaf blocks with cutout textures cast shadows that match the block's texture, allowing for nicely dappled light when inside a forest. Before I continue, I quickly want to talk about our sponsor, us. As most of you will know, making video games isn't cheap or easy, and for PlanetSmith to be the best it can be, I need to expand the team. So my plan is to run a Kickstarter later this year once I think we have enough people excited about the project. A lot of you have been asking how you can play the game. This will be your chance. Along with the Kickstarter, there will be a public demo anyone can play. Of course, this is a very early game build, so think of it more of a tech demo than a full game. It's just proof that what I am promising is possible. With the Kickstarter, there will be a way to pre-purchase the game. This will be the cheapest way to get your hands on the full version of PlanetSmith at launch. Also, there will be a limited number of slots to get alpha access to the game right now. You will become an alpha tester and get updates as they happen. I haven't decided what all the rewards will be yet, so if you have any good ideas, please share them on our Discord. If this is something that interests you, please follow PlanetSmith on Kickstarter, as this lets me know how many people are excited for this. I will only launch the project if I'm confident we can reach our goal. Links are in the description. If Kickstarter isn't your thing, but you still want to support PlanetSmith, please consider wishlisting the game on Steam and subscribing here on YouTube, as this helps us reach more people. Right, back to the lighting. The real-time shadows is something I love about the game, and it is a must-keep. But there is an issue. I want players to have the ability to add lights to the game. This may sound simple. Just add a light source every time a player places a torch. But it isn't that simple. To understand why, we need to understand how light and shadows are calculated in the first place. Lighting is one of the hardest things to get right in games. It can make or break games, and there is no perfect solution. You have to make compromises in order to get good frame rates or great shadows, and balancing this is the key. One of the most common tricks games make is to bake the lighting into a texture. This way, none of those hard lighting calculations have to be done at runtime. However, this means that the world has to be static and can't change. Obviously, in our Voxel world, everything can change at any point, so this option is not available to us. A good starting point is looking at what Minecraft does, as they have already solved this problem. Minecraft uses a per block light level system. The lighting data is stored as a byte for each block, with 4 bits for skylight and 4 bits for block light. This gives light levels of 0 to 15 for both skylight level and block light level. Skylight determines how much of the sunlight a block receives. If a block has nothing above it but air, it gets a light level of 15. Then, for every block that can't see the sky, it gets a light level of 1 less than its neighbor. Block light is light given off from blocks. Light skylight, it starts at 15 for the light source, or less for some light blocks, then goes down by 1 for each block away from the light source. The game then determines which light level is the highest, and then multiplies the block color by this light level to get a final color for the block which is displayed on your screen. The great thing about this technique is that it's really fast to calculate, and it doesn't matter how many light sources the player places, the render time is unaffected. However, it has some major drawbacks. First, it can't render shadows, just light and dark. This technique turns light into more of a liquid that can even flow around corners, and lighting things it shouldn't be able to. Also, light sources can't illuminate anything further than 15 blocks away, and this technique, light falls off linearly instead of the more realistic 1 over the radius squared. So what about real-time lights, like we see in almost all of the 3D games you play? Well, most games use forward rendering. I'm not going to do a full breakdown, but what this means for lighting is that each mesh is rendered once for each light that illuminates it. This means for every light we add, the complexity of the scene increases linearly. So if a player adds 10 lights, the scene is 10 times harder to render, and 100 lights, well, then the frame rate will drop to single digits on even the most beastly hardware. To remedy this, inside the shader, a normal technique is to only allow 4 lights to affect one mesh. However, this has the consequence that after the player places 4 lights, all the other light sources will not work. This isn't great either. So another option is deferred rendering. This works slightly differently, as all objects are rendered without any lighting first. Then, as a last step, lighting is calculated for each screen pixel. This means that the number of calculations is only per pixel per light, which is a lot faster when you have lots of lights. This sounds good. However, it comes with a couple of drawbacks of its own. It doesn't allow for anti-aliasing, at least without some workarounds, which aren't great. And you can't have transparent objects like water. This could work. I could stylize the water so it isn't transparent, but I would prefer to not have to do that. Instead, I have chosen to use a relatively new method, forward plus rendering. This works in a similar way to forward rendering, but uses a clever method of culling and storing only lights that contribute to the pixel, greatly reducing the workload. So we have a solution for our rendering. All that's left to do now is to get the light into the world when a player places a block with a light source. My solution for this is to add a flag to the block properties that lets you assign a prefab. Prefabs work using game objects, so all this code can't be executed inside a job. Instead, this must be done on the main thread. We must be very careful which blocks we allow to have prefabs, as they will cause a much greater performance hit. To help with performance, I'm creating a pool for prefabs. This is a little trick I like to do with a static class that keeps track of all the prefabs. This way, it can be accessed from any chunk. I will run you quickly through how it works. This is a list of queues for each type of prefab. There is one queue for each prefab type, and this is where I store the pool of unused prefabs. This get function retrieves a prefab instance. The index here refers to the index of the prefab we are wanting. For example, our light prefab will be index 0, but as I add more prefabs, the number of different prefabs will grow. First, the list of queues is expanded to be as long as the current prefab index. If the index is already included, nothing will happen. Then, I test to see if the queue for the prefab we want has any objects in it. If it does, it dequeues that object, sets it to active in the scene, and returns it as a new prefab instance. A prefab instance is just a container class to keep track of the prefab index. Otherwise, we instantiate a new copy of that prefab and return that as a new prefab instance. If a prefab is deleted or a chunk is unloaded that contains a prefab block, this return function is used to add the prefab back into its respective queue so it can be reused later. This is much more efficient than deleting and remaking. Finally, because this is a static class, meaning it won't be destroyed with the world, we need to clean up all the queues if the scene changes, as this will delete the pooled prefabs. I still want the majority of the calculations to happen inside jobs, so now, after a chunk update, I run the calculate prefabs function. This is a job that calculates all the changes that need to be made and stores the required additions and deletions into two buffers, which can later be executed on the main thread. Voxel objects is a list of all indices for the current prefabs in the chunk. Prefabs is a list of the required prefabs for the chunk. I then compare the two lists and add any removed objects for deletion to the removal buffer and any new prefabs to the additions buffer. Then, when the jobs resync with the main thread, I retrieve the additions and the removal buffers and add and remove the prefabs as requested. The sun has just set. Let's see what the new torch looks like. It's giving off a nice glow, lighting up the whole area. As I add more, the brightness increases as the lights are added together. I can remove torches as well, and the light is deleted correctly. Let's try digging down into the ground, and I'll place a torch down here. It lights up the little cave nicely. Now, there is one thing I'm not happy about, and that is the torch effect. It's just adding light, but it would be nice if it gave some embers off and had a flame. Back in the editor, I have created this animated flame, and also this particle effect that looks like embers. One thing I have to be very careful about is performance, so the flame needs to be very cheap to render and process. The mesh for the flame is as simple as it can be. It's a quad. The flame texture comes from some fancy shader trick. I saw this trick a long time ago, but it was using a script to update the shader, and that just wouldn't be performant enough for us. I have instead written it so it's all calculated inside the shader instead. The other thing the shader does is constantly billboard the quad to always face the player. However, because we're on a spherical world, that isn't simple either. Normally, your up axis doesn't change, but as we go around the globe, the flame needs to be aligned with the world's local up. The way this trick works is by using these textures. The top texture is scrolled upwards by the shader, and this gives the flame its flicker. These three textures are multiplied together into a grayscale image, and that forms the flame. Then, the last texture is remapped to the grayscale image, giving the flame its color. This means I can quickly swap the palette texture to get other cool flames. Looking at the shader code, the vertex shader gets the world position of the flame. It also gets the current time and offsets it by the world's local position, so torches close to each other animate slightly differently. The UV2 coordinates are offset by the time input to scroll the texture and give us our flame effect. It then takes the vertices and billboards them towards the player using this complex function that was a bit of a headache to get it working correctly. In the fragment shader, all the textures are sampled and multiplied together, then the grayscale image is remapped onto the palette texture. I'm really happy with how the torch turned out. It performs really well, and I think it looks great. There's still a problem when you try to place hundreds of lights in the same area, but I have a plan to address this in the future by using a clever hybrid system that uses some of the block light tricks Minecraft does. Torches are definitely good enough for now, and I will save that problem for future me. As we run about this castle filled with the new torches, I'd like to shout out our YouTube members. Thank you for supporting the channel directly. Remember, if supporting us on Kickstarter is something that interests you, please follow PlanetSmith on Kickstarter. I will only be launching the project on Kickstarter if there is enough interest. The link is in the description. Also, remember to add PlanetSmith to your Steam wishlist and come join our Discord. That is the best place to stay up to date with all things PlanetSmith and ask me questions. Thanks for watching. I will see you all in the next video.